In this application of derivative techniques, we're going to find approximate values, good approximate values, using the fact that a fact that we learned earlier, that secants are approximate slopes and that tangents are exact slopes, and when the h value is small, that is close to 0, that approximation, so when that h value is small, getting close to 0, the approximation can be very accurate. This technique is actually, we're going to look at it kind of in the abstract here, but it turns out in applications that you have in your later courses, you use variations of this method to get to set up computer programs to solve a wide variety of problems, a very important wide variety of problems. Okay, so we have a drawing here that should look kind of familiar to drawings that we looked at when we were defining the slope of a curve and using secant lines to do that. So right here we have drawn the tangent line to the curve at x, and we have identified these distances at x plus h1, delta y, and dy, and you can see that these delta y and dy are not very close together. Whereas when we make our h values smaller, so now we're looking at x plus h1, then the dy is from here to here, and the delta y is from here to here, and they're actually fairly close. So you can imagine that as the delta, or as the h value gets smaller and smaller, perhaps we can draw it, that is, if we were right here, you can see that the dy and the delta y are actually very close together, and as h goes to 0, we're going to actually be able to see in examples that they get extremely close. So we're familiar with this derivative definition, the limit definition of the derivative. Let's rewrite that by multiplying both sides by h and assuming that this limit is gone but that the h value is small. So first we have removed the limit h goes to 0 and said that in that case f prime is approximately f of x plus h minus f of x over h, and then we have multiplied both sides of that expression by h to come up with this expression. Now, when we write it in this way, so the left side is approximately equal to the right side, that approximation is better and better as h gets smaller. Let's designate what the left and the right sides are. So the right side is actually our delta y in the picture above, the exact change in y, and the left side is our dy, which is the approximate change in y. So I've tagged the left side dy with an a for approximate, and the right side delta y as an e for exact. So let's see in practice how accurate this approach really is. So we started where we left off with this left side being dy and the right side being delta y, and now we're rearranging. We're leaving the f of x plus h alone and moving it to the left side, and we're adding this f of x over to the f prime of x. So we have this expression, the left side approximately the right side. So let's define a function f of x. F of x is going to be the fifth root of x, or x to the 1/5, and let's suppose we want to find f of 33. Now we know that f of 32, the fifth root of 32, is 2, so this should be approximately 2. Let's see how good an approximation we can get. So let's note that we're going to have this f of 33 be the left-hand side of this equation. So the 33 is the x plus h. And for us to be able to resolve things on the right side of the equation, what we need to do is we need to choose x so that when we f of x is exact. So that means we want x to be 32, since f of 32 equals exactly 2. So let's set this up now. So we've got it partly set up. Let's see where we are. So the 33, the approximation we're trying to find, that is always going to be our x plus h, and we showed just a minute ago why x needs to be 32, because then f of that is exact. So if we solve for h, we see that h is 1, and so now on the right side we can designate this 32 as x. This is x, the h needs to go here, and so we put the 1 there. Now we need to calculate our f prime of x to be able to figure out what this term right here is. And so let's do that. So f of x is x to the 1/5, f prime is 1/5 x to the minus 4/5. We bring the power down and reduce the power by 1, and then we're going to rewrite that as 1 over 5 times the 5th root of x to the 4th power. So the minus 4/5 power, the 5 in the denominator, is the root, and the 4 in the numerator is the power. We want to do that in a specific way. Take the 5th root first and then raise to the 4th power. So let's calculate what that is when we plug our x in. So we plugged everything in. We were trying to find f of 33, the 5th root of 33. We put the x here in the f prime, we put the h here multiplying, and then the x here again. So let's calculate the numbers. So the 5th root of 32 is of course 2, and 1 over 5 times the 5th root of 32 to the 4th is 1 over 5 times 2 to the 4th, and that's 1 over 80. So let's substitute the 2 and the 1 over 80 in. So if we substitute the 1 over 80 in for 1 over 5 times the 5th root of 32 to the 4th, the 1 in for h, we add 2, we get 1/80th plus 2, which is 161 over 80, which is 2.0125. The approximation you could find on your calculator for the 5th root of 32 would be 2.01234. So actually 2.01235, so it's actually, our approximation is actually only off by 0.00015, or 1.5 out of 10,000, which is very accurate. Now obviously you wouldn't want to use this method to find the 5th root of 33, you can just use your calculator. What we're trying to show though is that the secant way of approximating things can be extremely accurate, and what happens in later application courses is you want to use these secant approximations to set up a computer program on a mesh, for instance, to measure fluid flow throughout a region, and you're not able to calculate the derivatives everywhere, so you're going to calculate secant approximates, and as long as they're accurate enough, if your mesh is fine enough, this turns out to be an extremely accurate way to solve the problem. So I want to do one more application of this to show that we can get more accuracy if h is even smaller compared to our x value. So if we want to find the 7th root of 127, our x plus h is going to be 127. Our x would, of course, be 128 because we know the 7th root of 128 is 2, and that gives us our h value is minus 1. Our function is going to be x to the 1/7. When we differentiate that, we get 1/7 x to the minus 6/7, and we rewrite it this way with the 7 being the root in the denominator. So we take the 7th root of x first, and then we raise it to the 6th power. And if we plug in our x value of 128, we get, so if we calculate that, we get 1 over 7 times 2 to the 6th. 2 to the 6th is 64, and so that's 1 over 448. So let's plug everything in and see how good of an approximation to 7th root of 127 we can get. So we use this formula again. Our x plus h is 127, f is the 7th root, our x is 128, our h is minus 1, and f of x is the 7th root of x, which is 128. So plugging in, we get 1 over 148 times the minus 1 plus 2. Notice that this is a negative expression, so it's less than 2 as it should be. And so let's get an approximation for this. 895 over 896. Excuse me, that should be 895 over 448. So here's our approximation using this method, and now let's see what our calculator says. So we see here's what the calculator gives us, and we're extremely accurate. It's only off in the 6th decimal place, so it's accurate to almost to the millionths place. So we've shown two examples of using this method. In this case, we got it accurate to the 10,000ths place, and in the case where the h was smaller compared to x, we got it accurate almost to the millionths place. So let's tie this in with applications that you're going to see later. What you're going to do actually is use this version. F prime of x is going to be approximately, so what you're going to do is, in a large scale calculation that you're going to want to do, such as maybe fluid flow, you're going to want to find this over a large number of points, maybe millions of points across a three-dimensional grid. You're not going to be able to do that in the program, and you're going to use these approximations each time, with the h value being very, very small, and you're going to get very accurate approximations here, which are going to be very close to what you really want, close enough, and as you saw, we can get it accurate to the millionths place pretty easily, and with today's methods and a fine grid, we can even do better than that when necessary. So there's a good application for derivatives. We're going to look at some additional applications for derivatives in later videos.